Hi, welcome. 15.6 is our video today. This is take 4 on it, and but it's the last one for sure. It is the last one. Okay, paper view. Here we go. It's gotten dark, and so I hope that's not too dark to see. And so 15.6 triple integrals, just so that you know what we're finding. When we found the integral of f of x dx, what we were finding was the area under the curve. And I don't know if you remember, I'm sure you do, but here's my curve, y equals f at x. And I'm going to say this goes from B to A here. And what we found was that area. And that area is in 2 dimensions. I don't know if you remember, but if f of x was a mass density function, then you had a really, really thin wire. So there's my really, really thin wire. Thinner than this, though. I got it too thick when I drew it there. Then this gives you the mass of a super thin wire if you integrate. And so that's the... this is A to B, here, since I put that on there. Now, when we were doing double integrals over a certain domain, then the double integral would give us the volume under z, z equals the function in terms of the independent variables x and y. And I'll draw a lovely picture of this. No one laugh. Anyone who laughs, I can hear you. And so we had x, y, z. We had, that's on the z equals 0, right? And then this had some height for z. And so, and we could find then the volume of that. I don't know why I drew it like a cylinder, but that's what I did. And if f at f, x, and y is the mass density function, then that gives you the mass of a super thin plate. And so then you would be getting a super thin plate. The plate doesn't have to be a rectangle, but you would be getting the mass of a super thin plate. It's so thin that it's just in 2 dimensions. It doesn't have any thickness at all. And if the function is equal to 1, then we can find the area of D. So whatever D is, you can use this to find the area. And one I can think of in particular is that that we had in class is we had some kind of a polar rose, right? And that we did, and we found the seems like we found the area of one leaf is what we found. And then if you have a triple integral, then you're integrating over this. And so this was dx, that's in 1 dimension. dA, that's in 2 dimensions because that's area. And then dV, that's in 3 dimensions, that's volume. And so this gives some measurement. It's too hard to comprehend, but I was hearing other people on the internet, our book didn't call it, but calling it like a mega volume or something, because it's 1 dimension beyond a volume, whereas 1 dimension beyond area is volume, and 1 dimension beyond length is area, right? And so they were calling it like a mega volume or something like that. Anyway, and so that's in 4 dimensions. So this was in 3 dimensions, and these were both in 2 dimensions. And why that's kind of good to know is that it's a double integral, and it does find something in 2 dimensions. Well, that's the same here. It's a triple integral, and it does find some things in three dimensions. And that's if this is a mass density function, then it gives us the mass of the 3D shape. And so it doesn't have to be a super thin. That was what they call that, a lamina. it went with laminate flooring. So anyway, it doesn't have to be super thin like that. It can be a volume. And if this is equal to 1, then so it would find the mass of some figure, right, that you have. And if this is equal to 1, then it's going to find the volume of E. So this is not, I wish I could think of the name that guy called it. It was a mega volume for this thing in 4D. Okay, so if I'm trying to find the triple integral here, then the first thing I'm going to find, and it's not telling us what we're finding here, it's just asking us to practice finding our triple integral, and you're going to see that it's just the same as finding a double integral, just one more. And so this is in terms of z, with respect to z. So this is going to be the integral from 0, this is z equals 0, to z equals x plus y. And 6xy dz would equal 6xy, that's a constant, times z, from z equals 0 to z equals x plus y. So when we plug in here 6xy, and for z, x plus y, minus, and then when you do 0, you're going to get 0. And so this is equal to 6x squared y plus 6x y squared. And we've only taken one integral. I'm going to do the second integral now. So the second integral goes from dx, so this is x equals y, to x equals 2y. So it's okay to have two variables here that are yet to be integrated. X and y were yet to be integrated. And here it's okay to have a variable in terms of a variable that's yet to be integrated, and y is yet to be integrated. So we're going to have here 6x squared, that's the ice maker, plus 6xy squared dx. So 6y is a constant, so it's x to the third over 3 plus, and then 6y squared is a constant, and that's x to the second over 2. And we're going to evaluate that from x equals y to x equals 2y. So when I plug this in, so this is 6 over 3 is 2, and we're going to be putting in for x 2y. So here we're going to be putting in 2y. So that's 2y to the third is 8y to the third. So this is going to be equal to 2 times y times 8. I'm going to mess this up, aren't I? 2 times, no, have confidence. I'm not going to mess this up. Okay, 2y and then 2y to the third plus, and then 6y, which is 3, because when we divide there, so 3y to the second times 2y to the second minus, and I wish it was 0, do you? And so we're going to get here 2y, and we're going to put in y, so y to the third, and plus, and 3y to the second, and then y to the second. And so this is going to be giving me, that's 8 times 2 is 16 y to the fourth. 4 times 3 is 12 y to the fourth. And then here minus 2y to the fourth and minus 3y to the fourth. And so when the dust clears here, we're getting 16, take away, no, add 12. 16 plus 12 minus 2 minus 3 is 23 y to the fourth. coincidentally, they were all the same, and it's because these were the same. Okay, and then our last integral here that we're going to do, what is y equals 0 to y equals 1 of 23y to the 4th. So that's equal to 23y to the 5th over 5 dy. Sorry, I forgot the dy in there. But I was taking the derivative with respect, the integral with respect to y, the antiderivative. So from 0 to 1 gives us 23 over 5. Okay, so we did a good job on that one. They didn't tell us what we were finding here, just practice on finding a triple integral. And unfortunately, this is written on the back. I couldn't know how to do on my new, my printer up here. I didn't know how to work it. Okay, and so this is example 2. And so we have to set this integral up where E is enclosed by these surfaces. And so we have a whole bunch of Z's here, 2 Z's, and some Y's. And so I get to choose, because of Fubini's theorem, you would get to choose whether or not you wanted to integrate with respect to, if you wanted to integrate with respect to Z first or X first or Y first, and it doesn't matter. And so you get to choose, and you should choose whichever one seems like it would be the easiest. And so since if I was going to do with respect to X first, I'd have to solve these equations for X. So that wouldn't be easy because that would create square roots. But leaving them solve for Y seems natural. And also doing, solve for Z seems natural. And doing, oh, is this too small? Can you guys see that? Unfortunately, you can see through the paper and see the other side. Woo, 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 woo. And so leaving them solve for Z seems natural. Y going last seems natural because we know that Y is from 0 to 2. And so anyway, so that's kind of our story. Hold on, camera, are you gonna focus? It's all I know it doesn't like the shadow. And so I couldn't make the paper not be printed on both sides, unfortunately. So I want to draw this so that I'll know which one is on top and which one's on bottom. So I'm going to come over here and I'm going to draw. This is Z. Z would always go on the up and down axis and then X. And so Z equals X squared minus 1. So this would be crossing here at -1. And then 1 minus, so crossing here at 1. And do you guys agree that they should cross right here on the axis? And so, because if X is 1, if you put that in, you get Z as 0. And if X is 1, you put that in, you get Z as 0. And if you put in -1, then you get, so this is crossing right here at 1 and also at -1. And so, and this was the one that was Z equals X squared minus 1. Is that one right there. So I'm going to set this integral up. And on the very inside, I'm going to do Z equals, and I'm going to go from X squared minus 1, Z, not X. It's been a long day. So Z equals 1 minus X squared. And we have this X minus Y, and then we're going to go dz. And then it's natural to use X, and the X's go from -1 to 1. So X's go from -1 to 1. And then the Y's were given to go from 0 to 2. So dx and then dy. You could change it around if you wanted. I find it hard to change them around. That's the most difficult thing. They didn't tell me what I was going to be finding here. They didn't tell me if this was, and so we're going to call it the mega volume, the one dimension beyond volume is what we're going to call it. Whatever that is, I don't even know if it has to be positive. I think it could be negative because I think that's what this one is. And so here we're going to take the integral with respect to z. And so we have this z equals x squared minus 1, z equals 1 minus x squared. So y minus this dz. So this is x minus y z. And then from z equals x squared minus 1 to z equals 1 minus x squared. And then we're going to plop that in. And so this is going to be x minus y, and then the upper bound. This pencil is on its last. Minus the lower bound, so x minus y, x squared minus 1. So I'm going to multiply that all together. I don't know if I was clever. I think I could somehow, I could factor out an x minus 1. And I think that I could, I don't know, I might, if I was more clever, I think I could put this together and then multiply it and be a little bit less work by factoring, but I don't know, I'm too tired. So I'm going to be foiling twice. So x minus x cubed minus y plus x squared y minus, and then parentheses, x cubed minus x squared y plus y, and x minus negative x is another x. So that's 2x. Negative x cubed minus x cubed is minus 2x cubed. Negative y minus y is minus 2y. And there's also 2 of these, they're positive. Positive 2x squared y. So we've taken one of the 3 integrals, and so now we're going to do the second integral. And that second integral is going from x equals negative 1 to x equals 1 of 2x minus 2x cubed minus 2y plus 2x squared y, and this one is dx. And so we're going to take the antiderivative. So this is 2x squared over 2. So that's gone. Minus 2x to the 4th over 4. Minus 2yx. Right, because y, that's just a constant. And plus 2yx cubed over 3. And we're going to be doing that from negative x equals negative 1, x equals negative 1, to x equals positive 1. So up bound minus low bound. So when we put in 1, we get 1 here, minus half. Putting in 1 there gives us minus 2y. Putting in 1 here gives us plus 2/3 y minus, and then putting in negative 1 and squaring it gives us 1. Putting in negative 1 and raising it to the 4th gives us negative 1/2 there. Putting in here gives us positive 2y. Putting in negative 1. Putting in a negative here is going to give us negative 2y over 3. So when the dust clears, 1 take away 1 is 0. Negative half plus half is 0. Negative 2y minus 2y is minus 4y. 2/3 plus 2/3 is 4/3 y. So, oh, and those are like terms, aren't they? They're both y. So, negative 4 plus 4/3 is negative 8/3 y. Sorry, I didn't see that those were like terms. And so now I'm on the last integral, and the last integral goes from y is 0 to y is 2 of negative 8/3 y dy. So that's negative 8/3 times y to the second over 2. And we're going to evaluate that from 0 to y is 2. So this is negative 8/3 times 2 squared over 2, which I think is negative 16/3. Okay, so we did a lovely job on that one, finding the, the mega volume or whatever you want to call it. This is example 3, and they're asking us to use a triple integral to find the volume. Because they're asking us to find volume, we're going to have triple integral 1, 2, 3, and for our we're going to integrate 1 is what we're going to integrate, because we're going to be finding the volume. And so anyway, so that's kind of the story there. So our function is equal to 1 because we want to find the volume. And so I want to figure out how I could set this up. Should I try to draw a picture of it? I know that that I have a paraboloid along the y-axis. I'm not very good at drawing the pictures of them. You guys are better at drawing the pictures of them. But I have something like this going, and then I have something out here at 8 and coming back this way. And somehow they're going to hook up probably there. And so that's the kind of thing that I have. Try to make it look three-dimensional, if you would. And so, but that's kind of something that I have. So what I want to do to get this set up to find the over the region that we're going to be integrating over is these are both equal to y, so you want to set them equal to one another. So that's x squared plus z squared equals 8 minus x squared minus z squared. And when you add, you're going to get 2x squared plus 2z squared equals 8. And so dividing by 2 gives us x squared plus z squared equals 4. So it's natural for us to integrate with respect to y first. I keep bumping the table, and I really apologize, and so that makes my camera shake. That doesn't happen at home because I don't have my camera on the table. And so I want to integrate with respect to y first. So when I set my integral up, this is going to be my volume. Now, if you're trying to figure out, well, which one would you put first? Would you put y equals x squared plus z squared, or would you put y equals 8 minus x squared minus z squared? If you look at where this intersection was, and it's at a circle with radius 2, and you can take any point on the circle, and I'm going to take 0, 0 right in the center. This is z here and x here. If I take 0, 0, and I put it in for x and for z, x is 0 and z is 0. This one's going from y is 0, and this is going to y is 8. So it is this one first. Y equals x squared plus z squared, and y equals 8 minus x squared minus z squared, z squared. Then, in order to do the bounds, so this is 1, because that's what we're integrating over, and this is dy. In order to do the bounds for x or z, you would have to solve this equation for x or for z and have square roots in it, right? If I solve for x, I would be getting z on the other side, so it was 4 minus z squared, and then take the square root, and it would be from minus the square root to the plus square root, and that would be for I had solved for x, so that would be for x's, and that would be really, really hard. And so we remember that if things are circular, that instead you can use polar, and the good news is that that you can say that x equals r cosine theta, and that you can say that z equals r sine theta. And so you can just go with what you have there, and that you can say that x squared plus z squared equals r squared. So that's going to be my plan on the polar. So this is going to be r squared equals 4, or that r equals 2. And so we're going to go here, r equals 0, because it's going to go from 0 out to 2. R equals 2. And remember, you always do, so this is going to be r dr d theta. And then we're going to go all the way around, so that's theta equals 0 to 2 pi. So now we have set it up. It would be okay to integrate and plug in what we have for y, but it's also okay to realize that since we're going to polar, that y equals r squared and y equals 8 minus r squared. So I think I'm going to do that when I set this up. So I'm going to have y equals r squared and y equals 8 minus r squared. And you can save the r if you like, or you can put it in here. You could have 1 r. Taking the antiderivative with respect to y. I think I will put the r there because I know that when I did this problem earlier all by myself, I forgot the r, and just because it got lost. And so when I integrate with respect to y, this is r is a constant times y. So this is going to be from y equals r squared to y equals 8 minus r squared. So this is equal to r 8 minus r squared minus, and then r squared. So this is equal to 8r minus r cubed minus r cubed. And so this is going to be 8r minus 2r cubed. And we've taken one integral, and we've got to do 3, and then we'll have found the volume, because we said that we'll find the volume of this two paraboloids coming together, intersecting one another. And so I didn't draw them too well. I don't know if I can make them look more, if I can make it look a little more 3D. So the next integral is r equals 0 to r equals 2. And we have 8r minus 2r cubed dr. So that's 8r squared over 2 minus 2r to the 4th over 4, from r equals 0 to r equals 2. And so when we plug this in here, I'm going to put that down below because that's going to be in the way. So here I'm going to get 4 and then 2 squared minus half and 2 to the 4th, and then minus 0. And I'm sorry, I don't have my regular monitor, so I keep going off the page, I know, and realizing that I've gone off the page. I really apologize. So 4 times 4 minus half times 16 is 8. So this is 8 So the last thing to finding our volume is from theta equals 0 to theta equals 2 pi. And we're integrating 8 d theta. And so that's going to give us 8 theta from 0 to 2 pi. So we get 16 pi as the volume of this paraboloid thing. I don't know. Looks like a torpedo now. Okay, so that was example 3. This is example 4, and our last example here. And they've asked us to write it 6 different ways, and I'm not going to do it 6 different ways. I think that's crazy. And so, but maybe we'll try it more than one way. So they're not asked. We don't have to integrate here. It's just set up. And so they're giving us x is 2, y is 2, z is 0, and x plus y minus 2z equals 2. And you can pick any variable to be your first. So I usually pick z is what I usually pick. And so, but it's not necessary to pick z. And so I'll show you z, and then we'll pick another one and we'll do the other one. So if I do z first, then what I'm going to have to do is I'm going to have to solve this equation right here for z. So that would be minus, well, I'll add the 2z to the other side. That will be clever. Okay, so I'm solving for z. So if I add the 2z to the other side, I'm going to get x plus y, and I'll take away 2, equals 2z. And then I will divide by 2. And so this is x plus y over 2 minus 1 equals z. Not necessary to be the way to write it, but it's an okay way of writing it as well, right? I divided this whole thing by 2 and that by 2. So now when I go to set up my integral, I'm going to first and I'm just going to put f, and I'm going to do dz. So I want to know, does z is 0 go first here, or does this go first? And so how you can tell on that is look at what you have. Now, when z is 0, that's when we're projected back to the xy plane. So that's when z is 0. So when z is 0, I'm going to put it in here, right here. Then my main equation is x plus y equals 2. This is when z is 0. And just kind of drawing the picture here at 2 and to 2 here is this line right here. What else do we have? We have x is 2, so that's here, x is 2. And we have y is 2. And so we want the area that's trapped by all of the things that we have. So that's our area right there. So if I pick a value in this area, then that will tell me which one the lower is, which I'm suspecting it's z is 0. And so this is over here, let's say 1 3/4. And then I want to make sure that I'm up above that line and picking a point. I don't know, 1 3/4 ought to do it, right? If I did 1 3/4, 1 3/4 ought to do it. And so if I put that in here, 1.75 plus 1.75 divided by 2 minus 1 I get 3/4, which for z, which is higher than 0. So that's if you're ever confused, you can do that. So z is 0, and z equals x plus y over 2 minus 1. Okay, so that's the inner. Now I want to do, and I can do either x or y, it doesn't matter. And so if I choose to do dx, then that means I'm going to be going from here to here, right? So that line needs to be solved for, excuse me, I'm going to be going from here to here, not there. That's not where the shading is, from here to here. That line needs to be solved for x. So this line is x equals 2 minus y. So if you decide to go, if you decide to do x next, I don't know why I wrote z, but if you decide to do x next, then you would come over here and go across. So you would go from x equals 2 minus y, x equals 2 minus y, to x equals 2. And then your y's would go from, it's everywhere that you would draw, so that's from 0 to 2. Y's would go from 0 to 2. Okay, so that's one of the 6 ways that there are. Another, so this is 1. I'm not going to do 6. So another one could be the same thing, z equals 0 to z equals x plus y over 2 minus 1 of our function dz. And then instead, we could have solved this equation and gone the other way for y. So we would have been going from here up to there. And so our equation would look like y equals 2 minus x. So it would be going from y equals 2 minus x to y equals 2. And then our x's just happen to be going 0 to 2 as well. So this would be dy dx. So that's a second way. If you wanted to do dy, and then I won't do any more because I think I will be bored of this situation. But if you wanted to do dy, then the y's start here at 2, and you would have to solve that equation. You'd have to solve this equation for y. Okay, so if I wanted to, I could solving for y. And let's see here. Solving for y would give y equals, and then it would be, I'm taking that equation, so I have 2, and I'm minusing x, and I'm minusing 2z. Okay, and then so we're going to run, it's either going to go from this to 2, or it's going to go from 2 to this. So I got to figure out which one. So over here, I should have z and x, and this is the xz plane, where y is 0. So if y is 0 in that equation that you had, x plus y is 0 minus 2z equals 2. And so I want to graph that line right there. I ought to be able to do that without picking points, but it's been one of those days. Reflexes, put x there, and not z, put y there. So if z is 0, then we get 2 for x, and if x is 0, then we get -1 for z. And so 2, 0, and 0, negative 1. So we have this here. How could I made a mistake there? But I did. 2, take away x, this should have been plus z, plus 2z. And so when y is 0, oh, y's not 0. That's what I'm doing wrong. And I was like, I had done this problem before. And what's y, friends? Y is 2. So I really want to be, I don't want to be on the xz plane. I want to be on the plane where, I don't want to be where y is 0. I want to be where y is 2. And it's so natural to, most of them are 0. Well, z was 0, but a lot of them are 0. But when y is 2, and then I was like, I remember that when I drew it wasn't in the fourth quadrant there. It was in the first quadrant, and most of the time they have things in the first quadrant. And so when it's ending up somewhere else other than the first quadrant, I'm like, what am I doing wrong? Because that's typically where they put it. Okay, so when y is 2, we get x plus 2 minus 2z equals 2. So that when we take away 2 both sides, we get x minus 2z equals 0, or x equals 2z. And so when I was thinking I was going crazy, when x is 0, z is 0, and when z is 1, x is 2, and let's see what else we know. So we have this point here at 0, 0, and then we have this point over here 2, up 1. And so we have this line here. And so, and we have also x is 2, so that's this line here. And we also know that z is 0, so that's this line here. So this is our region that's being trapped. And so if you pick any point inside this region, like if you pick 1, but you want to make sure that you don't pick, something on the boundary. And so you want to make sure that you get it fully in the region. Maybe I'll pick that point right there. That point that I'm choosing right there has the ordered pair 1.5, and it can be any height up, and so I'm going to call it 0.2 up, and so this is x and this is z, and I'm just doing that just so that I know what comes first. 2, right? Y is 2, or y is this. And so when I put this in, I get 2, take away 1.5, plus 2 times 0.2 for z, and I got 9/10, and 9/10 is smaller than 2, so this is the lower bound. So do you guys see how I did that? I picked a point in this region, and then I figured out, was y equals 2 bigger or smaller for for any point. It should be the same for all of the points. So that's going to be my lower bound, because when I put in a value in here, that got me 9/10 and to 2. And it should be for every value in there. Now I'm going to go, so this is my F. And what did I say I was doing first? dy, right? So because I already did the y's. And then now it doesn't matter if you do x. So if I do x, this is already solved for x. So this is going to go from x is the, don't do that, Donna. This one right here, as you go across for x, you're going to hit this first. So that's x is to z. And then you're going to go hit over here where x is 2. And then for z, our z's are going from 0 to 1. So this is dx, dz. So there's a third way. There's 6 of them all together, and you can see the pattern. So if you wanted to do the one for x, you're going to be solving for x, and you're going to be letting x be 2 and doing this picture like that. And so kind of the same idea anyway. And so it would be, if you want to challenge yourself, you can give it a try. Anyway, okay, that's enough.